Hi. Intermolecular forces are the last chapter in College Chemistry 1. This is a very easy chapter, and I hope you will enjoy it. I like these chapters where you can see all around you what we are explaining in chemistry. This one of, well, I like chemistry, okay? So, if you remember, in the gas chapters, we used the kinetic molecular theory to explain gases. And what we're going to be doing here is applying that to explain the behavior of solids and liquids too. Especially when we're dealing with solids, we're going to be talking about particles because we're not going to differentiate whether it is an atom or a molecule or an ion. The attraction between these particles, we're going to call it intermolecular attraction, but again, keep in mind they may not be molecules, they could be ions, something like that. And this is going to explain the difference between the three states of matter. In a solid, the parts are going to be very tightly packed together. Very often they're going to be arranged in a regular pattern. In the liquid, they're closer, but there's not a regular arrangement. They can move, they can flow around it. In a gas, there is no attraction whatsoever. They're very far apart, no arrangement, nothing. Also, the behavior of the particles changes depending whether you're in a liquid, solid, or gas state. In a solid, the particles vibrate about fixed positions, but they don't usually move. Remember, solids have a fixed shape. Okay? A liquid is going to adapt to the shape of a container, so the particles can move past each other. They're still in contact, but it's a looser contact, so they can change shapes. But in the gas, they're going to be independent. The only time they interact with each other is when they collide. I like to compare that to students. I've been teaching college for a long time, and college students tend to stay in their seats in class. They may not be paying attention. Maybe they're looking at their phone to see what time it is, or texting a friend. I had students playing cards on their laptops, but they stay in their place. Okay? One year, I don't know how I got caught into that, but they asked me, would I teach a biological sciences class for middle school? And that was a nightmare because those kids did not stay sit very long. They were constantly getting up to check on each other, to bother each other. They drove me nuts. That's not the way I remember middle school when I was growing up. And 2 years, that was actually real fun that I volunteered. I taught Spanish to kindergartners, K4 and K5. Those kids were smart. You won't believe how easy they can learn a new language. But they did not sit for a second. They were constantly moving. And the teacher warned me, it's okay. They're used to that. They're moving, jumping, doing whatever it is, but they're listening to you. That's the difference between a solid, a liquid, and a gas. Okay? So we're going to be talking about forces, and basically we're going to differentiate between intermolecular, meaning between molecules, versus intramolecular. They're inside of the molecule. These are the forces that hold the atoms together in a molecule, and we've been talking about them for a long time when we talk about bonds, ionic bond, covalent bond. This chapter is going to be about intermolecular forces, the forces of attraction between atoms and molecules. And 2 points that I need to make before, so there's no confusion later on. Intermolecular forces are always the result of electrostatic phenomena. Okay? There is no covalent, they are all non-covalent forces. You know when you add heat, let's say you have an ice cube. When it warms up, it melts. If you warm it up further, it evaporates, right? So when you add kinetic energy, you overcome the intermolecular forces and you can switch from one state of the matter to other. This is an example to compare intermolecular versus intramolecular forces. You have hydrogen chloride, and we talk about this bond in particular, and we said this is a polar covalent bond. It's a covalent bond because they are sharing a pair of electrons. It's polar because chlorine is very electronegative, which means that the chlorine has a partial negative charge, the hydrogen has a partial positive charge. So if there's another molecule, it's obviously opposite charges are going to attract each other. So these molecules orient themselves, and you have a weak attraction between the hydrogen of one molecule and the chlorine of the other one. Like I said, it is an electrostatic attraction, but it's very, very weak. Why do I say it's weak? Well, electrostatic attraction is directly proportional to the charges, inversely proportional to the square of the distance. These are teeny charges. If you remember, one charge when we're dealing at the atomic level is unbelievably small. You remember when we define the unit. And this is not even a whole charge, it's a partial charge. So the charges are very, very small. I'm not going to say that the distance is big, but it's more than the distance in a bond. So very small numerator, larger denominator, is a very weak force. But it's a weak, never a force. And because it's between molecules, we call it intermolecular. So like I said, we can explain the transition between solid, liquid, and gas when you increase the temperature, because you are overcoming the intermolecular forces. The strong intermolecular forces hold solid particles together in a solid, but as you increase the temperature, you start overcoming, you get weaker and weaker intermolecular forces, so you have a liquid and you have a gas. Now, the strength of those intermolecular forces depends on the substances, obviously. They're always significantly weaker than the intramolecular forces. But because there's so many of them, they're going to become extremely important. Okay? So just wait. Like I said, this is an interesting chapter, I think. We're going to see three different types. You have dispersion forces, dipole-dipole attractions, and hydrogen bonding. And all of them together are referred to as the van der Waals forces. Remember van der Waals? He's the one who wrote the equation for gases where you corrected for the volume of the molecules and you corrected for the weak attraction between the molecules. So you can tell it comes together. He was working between attraction and he realized the ideal gas law need to be corrected for that. It's the same fellow who did the equation. So let's look at the first type, dispersion forces. Very important. All substances have them. Okay? It doesn't matter what type of substance. They're also known as London dispersion forces. Again, some people like to name after the researchers who work on that. And it's due to the fact that all molecules are made up of atoms. All atoms are made up of protons, neutrons, and electrons. So the motion of electrons causes instantaneous dipoles. What is instantaneous dipole? Well, look at the picture below here, the helium. Imagine that you're taking a video of the helium and you freeze the video. You stop and you're watching. Maybe by coincidence, because the two electrons were moving, they both happen to be on the left side of the atom. That means the left side of the atom is going to be slightly negative. You can see, making the right side slightly positive. So if that's the case and there's an helium atom, that small positive charge is going to attract electrons from the next atom. So you see, it induces a dipole on the other molecule. But this is instantaneous. You cannot freeze the atom. The electrons are continuously moving. So these instantaneous dipoles are appearing and disappearing, and they are causing induced dipoles to keep appearing and disappearing. They don't last very long. They're weak. So they're fleeting, temporary, weak, but they exist. Okay? They're kind of like the light on a Christmas tree that are blinking on and off, on and off, on and off continuously. But you can see them, right? So they do have an effect. Dispersion forces vary with several factors. One of them is the size of the atom, or the molar mass, because bigger, heavier particles are going to have a stronger, let me put heavier, than lighter ones and smaller ones. Why? Because the bigger the atom, the farther the valence electrons are from the nucleus, so the weaker the attraction between the electron and the nucleus is easier to polarize that electron. Okay, so that's polarizability, how easy or difficult it is to polarize, to distort the distribution of charges in here. So once again, if you have two atoms, one is small, the other one is bigger, obviously there's hard layers in here, there's a bigger distance, this electron here is going to be easier to polarize because it's farther from the nucleus that's holding it in place. And how do we measure dispersion forces? Well, one easy way to measure them is looking at melting points and boiling points, because we said you have to overcome the intermolecular forces to melt a solid or to boil a liquid. So the harder the forces, the more heat you have to give them. Notice these halogens in here. If you look at the molar mass, it increases. Look at atomic radius increases. The same thing with the melting points and boiling points. So you can see the bigger the molecule, the more heat you have to give it. Why? Because the stronger the intermolecular forces. Okay? That's not the only factor. The shape of the molecule has something to do. You have here some isomers of pentane. I don't know if you can really see, but pentane is C5H12. But neopentane, it has CH3, 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 CH3. Okay, so you can see it's a very compact, almost rounded molecule. Isopentane, and I'm going to put it in here where I have room, you have actually two, so CH3, CH3, CH, CH2, CH3. So it's a little bit less rounded. And N-pentane is completely linear. So SH3, CH2, 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 CH3. So you can see how you go from an almost random molecule to a linear molecule. And it's very easy to see in the drawing how the area of interaction between two linear molecules is much bigger than the area of interaction between the two circular ones. So since dispersion forces are between atoms that are close together, the bigger the area of close contact, the bigger intermolecular forces. And you can see the boiling point, 9.5 times Celsius, 27, 36. The longer the molecule, the longer the surface of interaction, the higher the boiling point. We said the second type of forces was dipole-dipole. This time we are talking about not temporary dipoles, but fixed dipoles. We are talking about polar molecules. Polar molecules have dipole-dipole attractions. Remember hydrogen chloride. Okay? So if this was hydrogen chloride, this would be the hydrogen, this would be the chlorine, hydrogen, chlorine. These are stronger than dispersion forces, even if there's no other reason, because these dipoles are not temporary. They stay in there. They're not on and off, appearing and disappearing. They're not random. They are there continuously. Okay? Now keep in mind that polar molecules, they also have dispersion forces. So they have two types of intermolecular forces. Intramolecular forces. Intermolecular forces. That causes the molecules to orient themselves so that opposite poles attract each other and all of that. That's fine. Just remember they're stronger and they're added to the regular dispersion forces. If you compare two molecules that have similar mass, one is polar and that one is non-polar, you're going to see that the polar molecule, because it has two forces in there, is going to have strong intermolecular forces. So look at hydrogen chloride and fluorine. You know this one is polar, right? We use this example over and over. Fluorine is non-polar because it doesn't matter what the electronegativity of fluorine is, the difference between fluorine and fluorine is going to be 0. So it's non-polar at all. But that's the main difference between them. They have the same number of atoms, they have very similar molar masses. The difference is hydrogen chloride is going to have dipole-dipole attractions and dispersion. Fluorine is only going to have dispersion forces. So you'd expect the boiling point to be high for hydrogen chloride. 188 Kelvin, fluorine, chloride, sorry, gas, 85 K. So being a polar molecule increases the boiling point, indicating you higher intermolecular forces. Now we're going to look at two molecules that you may not see at the beginning as being similar, but nitrogen fluoride and water, you can tell that they're very different in mass. One is 49 MUs and one is 18. So you'd expect the biggest one to have stronger intermolecular forces, to be a solid probably. Since you know what is liquid room temperature, you don't expect the other one to be a gas. So, no, that doesn't make any sense. It's a bigger molecule, should have stronger intermolecular forces. It should be either a liquid with a higher boiling point, with a higher melting point and boiling point, or it should be a solid. But no, it's a gas. How do you explain that? Now, we talk about, mass does not explain it. You cannot use shape because they have about the same shape. So, how about the dipole moment? Maybe one has a stronger dipole moment. No, when they measure, they're very comparable. We have a problem, don't we? We're going to see that the difference in the boiling points, and I didn't mention the boiling points, sorry. I went over that so quickly. I don't even know if I have. No, well, obviously one's gas, one's a liquid. I don't have the actual numbers. But the difference in boiling points is due to a particularly strong dipole-dipole attraction that we call hydrogen bonding. Now, to have hydrogen bonding, you have to have a hydrogen, obviously, and it has to be bonding to a very electronegative atom. So fluorine, oxygen, or nitrogen, those are the most common ones, because they're the most electronegative elements. So in the case of water, obviously, you do have that. You have hydrogen bond to oxygen. In the other molecule, you don't have that. So this is going to form hydrogen bonds, the other one doesn't. Even though the other one, let me give you the formula, ONF, you have oxygen, nitrogen, fluorine. They both are very electronegative, but they're missing the hydrogen. You cannot have a hydrogen bond with a hydrogen. Okay? Basically, the idea of the hydrogen bond is you have a very large difference in electronegativity between the hydrogen and whichever atom is attached to, and also both the hydrogen and their atoms are very small, so it leads to very highly concentrated partial charges. That's what causes hydrogen bonding to be so strong. And once again, the word molecule does have hydrogen bonding, this one doesn't, so that explains the difference. So hydrogen bonding is present only on certain polar molecules because they have to have the hydrogen attached to a very electronegative atom, and it's actually the strongest of all the van der Waals forces. Again, because not only is very polar, but the charges are very concentrated. So looking at the water molecule, and you can see each water molecule can form 4 hydrogen bonds. Because oxygen, that's slightly negative, can form hydrogen bonds with 2 different hydrogens. The hydrogens are going to form hydrogen bonds with the oxygen of another molecule. So let me give you an idea. If you have but have 0.6 ounces of water, that's about, it's not exactly, but you could just call it's about 18 milliliters or 18 grams. You can call it 1 mole of water. Okay? So you know you have 6.022 times 10 to the 23 molecules. Now, each molecule can form 4 hydrogen bonds. So you realize in half an ounce of water how many hydrogen bonds you can form? That's why hydrogen bonds, they're still intermolecular forces that are still weak compared to ionic or covalent bonds, but there's so many that they become very, very significant. We're going to look at just 2 examples. I don't want to spend too much time just talking about water. If you're curious about how hydrogen bonds are responsible for all of the properties of water that allow life, I do have a chapter in my biology section where I expand on water. But I'm going to just give you 2 examples on hydrogen bondings and life. You know water expands when it freezes. That's the only substance that, instead of contracting, when it freezes, it actually expands. That's the reason you put antifreeze in your radiator, because if the water froze, it would burst the radiator. That's the reason when it's very cold, you let the water run in the pipes, so the pipes don't burst, right? Why does water increase? Because the hydrogen bondings at the time of freezing separate the water molecules. They have to have a certain distance to form a crystal, so it expands the molecules. And you say, well, so what? I mean, you said that this is important for life, but all I can see is that it bursts my radiator, it bursts my pipes. What good does it do? Well, let me put it this way. You know, density is mass divided by volume. The amount of water, the mass, is the same way as liquid or ice, but the volume increases in the ice. When the volume increases, what happens to the density? Density decreases, and as a consequence, ice floats. That's very important for life. You don't think so? Well, that's because you're not a fish. If you was a fish in a pond, when the winter comes, the water starts freezing. Ice gets on top, right? So you have a layer of ice. Believe it or not, this ice on top actually acts as an insulator. So the rest of the pond remains liquid. Think about it. It doesn't take a very low temperature to get a thin layer of ice over the river or the lake or whatever you live. But it has to get very, 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 very cold for the ice to be thick enough for you to go ice skating. Why? Because, like I said, the ice is acting as an insulator. When I was a graduate student, I spent 4 winters in Washington, D.C. I wanted so badly to go ice skating on the Potomac. Every day I checked the ice report, because the Park Service reported on the ice they were going to announce when it was safe to go ice skating. Never did it. It never got cold enough. It got very cold. It was never cold enough to ice skate. Again, the ice on top makes it harder for any more water to freeze. So this little fish in here is going to be cold, it's going to be uncomfortable, it's going to survive. What if ice did not float? What if ice did not expand, so it did not lower the density? Then when the winter comes, the whole pond would freeze. There's no protection, and that'll be the end of the fish. It would die. So many water organisms can survive because ice floats. So you have to agree to them, this is important. Okay? The other example I want to give you is hydrogen bonds are very important in maintaining the structure of biological macromolecules. Think on DNA. I know it's difficult to see, but you have one strand of DNA here, you have another strand in here, and they are connected by hydrogen bonds. How many? Depends on the bases. It can be 2, it can be 3 for every base. DNA is a very long molecule, okay? Just to give you an example I look at, of curiosity, the gene that codes for insulin. Okay? How many base pairs, or how many bases on one side? And it's 1,425 base pairs. Each base pair can form either 2 or 3. So you get the idea that this gene is not a really big one. Seriously, they're much bigger genes, but it's going to have several thousand base pairs holding the DNA together. Well, let's look at the protein. And there are other hydrogen bonds that can form in the protein, but we're looking only at the bond between two amino acids. Okay? It's called a peptide bond, and it involves a carbon hydrogen and a nitrogen hydrogen. So peptide bonds that are close to each other, and how close it depends on what type of structure you're actually forming, because there's different forms of folding the protein, but every peptide bond is going to form 2 hydrogen bonds. So some are going to form a helix, some are going to be folded like a map. There's many different, but they're all held together by hydrogen bonds. We was talking about the gene for insulin. When this gene is translated, and this is not the active insulin yet. Okay, I think I wrote someplace 110, originally has 110 amino acids. It's going to have to be modified before it's active, but you have 110 amino acids, so you have over 200 hydrogen bonds holding the structure together. Like I said, there's other hydrogen bonds we're not going to discuss in here. The point I'm trying to make is that biological molecules are held in the correct shape to work by hydrogen bonds. Again, hydrogen bonds, they may be the strongest of the intermolecular forces, but they're still weaker than regular bonds. But there's so many of them, they become extremely important in biology. So if you want to work one-on-one, I do have a worksheet where I give you different molecules to compare and put them in order of increasing boiling point or mention which type of intermolecular forces. I do have a nice worksheet that should be very similar to the question you find in an exam. If you make an appointment with me in Wysant, and remember the link is in the video description, I will share that worksheet with you, and you can practice before you need it for class.